Here we can see the result of our transient RC circuit simulation, where the circuit with the 10 kilo ohm resistor arrived at our 5 voltage output much faster than the 100 kilo ohm resistor. That's because the RC circuit relationship, capacitance times dV dt, or the change of voltage over time, is equivalent to the change in voltage divided by resistance. So the smaller the resistance, the faster we will arrive at that dV dt. The main part of my Arduino code are these for loops, which go from I to 500, which is 50 divided by the tau value. In them, I analog read both the voltage at the input and the voltage at the capacitor and string them together to display to the serial monitor. Our delay reads these values at varying intervals. The tau value itself from RC circuit theory is the product of resistance and capacitance. Here we can see on the serial monitor the voltage input varies between 0 and 5 volts, while the voltage of the capacitor gradually charges and discharges. This section of the processing code shows how I created my background and my legend by using the figure dimensions in a function. I crafted a simple RC circuit where we replaced the resistor with 10,000 ohms and 100,000 ohms. This is a 10 microfarad capacitor. For the 10 kilo ohm resistor, we can see the charging and discharging of the capacitor voltage as it appears in a traditional RC circuit plot. This is exactly as we expect, as we can see our concavity changes once it reaches its peak and once it reaches its minimum. For reference, I have a 5-second delay that occurs at the beginning of each time this code is run. This is to fully discharge the capacitor. Here I've added a 100,000 ohm resistor to the circuit. Due to the limitations of our 10-bit processing, I left the time constant unchanged. For the 10,000 kilo ohm resistor, we see a nigh-perfect graph of the input voltage and the capacitor voltage. You can see the capacitor charging and discharging, shown in red with the varying concavity. Our input voltage, which is a digital output, varies between 5 volts and 0 volts. For our 100,000 ohm resistor, we see a more atypical plot. Each step of the voltage input causes a decrease in the capacitor voltage, which levels off at around just over 3 volts rather than the 5 volts we would expect from the previous part. Nevertheless, we can still see how the capacitor charges through the same general concave manner. Now we've replaced the capacitor in our circuit with a thermistor. When the sensitivity of the output voltage is at a maximum is when we use the 10,000 ohm resistor rather than the 100,000 ohm resistor. Ideally, no resistor would be the maximum, but between the two of the lab, 10,000 is what we're going to roll with. The time constant I've selected is 15 seconds, as was taken from the data section of the data sheet. In my room temperature of 22.6 degrees Celsius, the voltage going through the thermistor is about 2.5 volts. When I pinch my fingers, which have a body temperature north of 35 degrees Celsius, we can see this voltage decreases. I have also left in the step of the voltage input, and we can see at 0 both voltages are 0. In order to cool the thermistor, I bagged ice cubes which have a temperature of around 0 degrees Celsius and touched them to the thermistor. We can see the voltage rapidly rise when the thermistor is in contact with this much lower temperature. From my understanding, this change in temperature acts as a step in the voltage function equation, and as heat transfer is always a function of time, we can see that this is not instantaneous and it has to gradually change. Commented Arduino and processing code will be available upon request. Thank you and have a nice day.